In this lesson, we're going to talk about vectors, and vectors are things that have both magnitude and direction. And if a quantity only has a magnitude, then it's called a scalar. So we could be talking about a vector, a car that's traveling at 50 miles per hour going south. And so we would represent the length of the vector would be the magnitude, and then the direction would be its direction. And we know that when there are accidents, the direction that the car is traveling and how fast it's going comes into play. So we could have this, we could have it going north and at 50 miles per hour. We could have one that was maybe only 25. So we would show it about half that distance because it has half the magnitude. So when we discuss vectors, we're going to deal with the magnitude, and when we draw them, the length of our line will represent the magnitude, and then we'll talk about direction. Now, to label a vector so that we know, we'll give the vector a name. And so we could call it vector v, and to show that it's a vector and not just a variable, we'll put an arrow over it. You could also make it in boldface if you were able to write it that way. To show the magnitude of a vector, we put it inside absolute value bars. And so we would talk about the magnitude of vector v. So up here, if we were going to call this vector v, then its magnitude would be 50. And we would have that represented. So we're going to be looking at our vectors. Now, vectors are said to be equivalent if they have the same magnitude and direction. So we could draw a vector and then if another one has the same magnitude and the same direction, then these would be said to be equivalent. So this could be vector u This could be vector v. So we could say that they're equivalent, or that vector u is equal to, and sometimes you'll see those as wavy lines to just say that they're equivalent, that they're different vectors, but they have the same magnitude and direction. Now, we could draw two other vectors. We could have vector r and then we could have vector s Okay, these have the same magnitude, but they don't have the same direction, so these vectors are not equivalent. So vector r is not equivalent to vector s because they have different directions. So we can talk about vectors being equivalent. Now, if we want to add vectors, there's actually two methods that we have for adding vectors. One's called the head-to-tail method, and one is called the parallelogram method. And it kind of depends upon the problem that you're doing as to which method is easier to use. And in some of our problems, we will use each of these depending upon the problem. But let's say that we have vector u and we have vector v. Now, if we want to add these together, let's look at the two methods. One is called, let me label these first so we'll know which one's which. We've got vector u and vector v. So if we want to add these together and we want u plus v, and we'll get a resultant vector, then what we'll do is this is called our head to tail. We'll take vector u and we'll try to draw it the same length and direction. Then, so it began here and it ended here. So then what we're going to do for vector v is we're going to start where that one ended, and we'll draw vector v. Where one ends becomes the beginning of the other one. And again, we'll try to draw it in the same distance. So we've got our vector u and our vector v. Now the resultant of these, the sum of these then, starts where u started, and it goes to where v ended. And this would be our resultant. So this would be our u plus v. That would be the resultant of that. And we'll use this type of addition when we're talking about navigation in planes with the wind acting upon them, where you have a force that's acting constantly upon the other one. The other method that we use is called the parallelogram method, and that's when you've got two forces acting upon something. So we could take these same two vectors, and using the parallelogram method, we would start. We'll draw our u, trying to get it the length. And then beginning at the same place, we would draw v. And then what we do is we make a parallelogram. So we're going to draw a line from here parallel this to u and the same distance, equivalent vector. And we'll draw one parallel to v. Again, we've got our u and our v. Now our resultant here goes from where they started. So this is where you've got some object and you have two different forces. If you had two people pulling something, well then they're pulling in different directions. And our result starts from here and goes to the end. So this would be our u plus v at this point. U plus v. And this is called the parallelogram method. Now notice the resultant's the same, and it's going off in the same direction. It's the same magnitude. So we can deal then with adding two vectors together. If we wanted to subtract two vectors, then let's take these same two, and we want u minus v. We want that vector. So we would draw u E. And I'm not measuring these, but just trying to get it about the same distance. Now, for minus v, what we do is we go the same magnitude, but we go the opposite direction. So it would go off in this opposite direction. And then we would have our magnitude from the beginning of this to the end. And so we had u, but this is the opposite of v. So this would be u minus v. And you'll have some vectors that you're to draw and show the addition for. Most of what we're wanting to do then is look at some problems and see how we would go about using our vectors with some navigation. So let's look at this problem. Get it down just a little bit lower here, except then my degree signs are not in the right place. Okay, we've got two planes take off at the same time from an airport. The first plane is flying at 260 miles per hour on a bearing of south 40 degrees east. The second plane is flying in the direction of south 50 degrees west at 280 miles per hour. If there are no wind currents blowing, how far apart are they after 2 hours? What is the bearing of the second plane from the first plane? Okay, we're going to draw this, and if you remember when we drew these before, we kind of had our north, south, east, west line. So I'm going to draw that here because we're going to be dealing from a point they took off at the same place. Now, this first plane is flying 260 miles per hour on a bearing of south 40 degrees toward the east. So we're going 40 degrees toward the east, and it's going at 260 miles per hour, which would be its magnitude. The second plane is going south 50 degrees toward the west. So we're going off in this direction 50 degrees, and it's going a little bit faster, so it's going to be a little longer than the other one. It will have gone further. All right, now we know that our distances are our angles here. This angle is 40 degrees, and this angle is 50 degrees, so what does that tell us? Yes, it tells us that we have a right angle. Now we're flying for 2 hours. So if we went 280 miles per hour and we flew for 2 hours, then we're going to have traveled 560 miles. Would be our distance. Whoops, that's the wrong one. We went 260 miles per hour. So that would be 520 miles. This one went the 560 miles. Okay, what we want to know, first of all, is what is the distance between the planes? How far apart are they? So we want to know this distance. And then we want to know what is the bearing of the second plane from the first plane. What is the bearing of the second plane from the first plane? Okay, so let's start with the distance. If we're going to find this distance, we know we have a right triangle, and we're just going to use the Pythagorean theorem. So we know that 520 squared plus 560 squared will equal x squared. So if we take the square root of that, it equals x. So if we look at our calculator, and let's make sure that we're in the degree mode. We're not using degrees right now, but we will be, so always check to make sure you're in the right mode before you start, because when you get to that problem, you may forget to check it then. So we have the second square root, 520 squared plus 560 squared. And so they're 764 miles apart. 764 miles apart. Miles. Okay, now we want the bearing of the second plane from the first plane. So what that means is at this point, and sometimes your pictures may not look exactly right, but what we want to know is from this point, if we drew our north-south line, now we know that this plane went further. So it's going to be down lower, so our east-west line would be above that. And your pictures may not always look exact, but we want to find the angle from here up to this side. Okay, so we need to figure up how, excuse me, it's not going to be above it. It's actually, this one's going to be below. Yeah, this one is below that. So we need to know how far below we are. So at this point, we've got to do a little bit of figuring of our angle. Okay, we've got our angle and we've got several parts here that we're going to deal with. And we use a lot of the parallel lines cut by transversals. So we know we have a north-south line here and a north-south line here. So from south to the line is the same as the line to, to north. Drew that the wrong way. From south to the line is the same as from the line to north. So we know that much is 40 degrees. And we actually know then we could have done this from east to the line is our line to here we know is 50 degrees. Now what we're going to have to do is to find this whole angle, and we know that whatever we have beyond 50 degrees then was below our west line. So to find this angle, we know the opposite side, we know the adjacent side. So we can say the tangent and we could call this alpha. The tangent of alpha, which is the whole angle, is equal to the opposite over the adjacent. Now we're looking for an angle, so the inverse tangent of 560 over 520 would equal alpha. Okay, let's look at our calculator. We'll say second tangent of 560 divided by 520 okay, that equals 47 degrees. Now, okay, I made an assumption up here that was incorrect. I said that it would go below this because we knew it went further, but it went off in a different direction, and so it doesn't necessarily go down below this line. It's just off in a direction. And so the very thing I told you not to do, make assumptions based upon your picture and the way that you drew it, we don't need to do that. So let's look back at it again. We got then that the tangent, that alpha, our angle for here, was 47. So if you look from the north, we've gone 40 degrees because of alternate interior angles. And then we went 47 degrees because that was our angle inside. So we've gone north, from the north, we've gone 87 degrees towards the west would be the direction of the second plane from the first. And so you can't rely on exactly how you've drawn your picture because we're not getting out tools, measuring, and compasses. We're just estimating our angles. And so you have to go back and rely upon the math. And if we had gotten an angle bigger than 50 degrees, then that would have meant that we would have gone beyond, and we'd know how many degrees we went beyond that. And we could have subtracted, and then we would have gone south, a direction toward the west. So you'll just have to look at each picture. Okay, let's look at another one. And we've got a boat is 2.4 degrees off course. If it is traveling at 12 miles per hour, how far off course will it be after 3 hours? So we want to deal and look at this and see just how far off course we would be from wherever we are. Now, we don't know which direction we're traveling, and it doesn't really matter at this point. If, let's say this was the direction we were supposed to travel. We're off course by 2.4 degrees. So instead of going in that direction, we're actually going off in this direction, and 2.4 is not very much, so I'm drawing it bigger simply so that we could see. And we're going to travel for 3 hours. So after 3 hours at 12 miles an hour, we're going to have gone 36 miles. And we were off by 2.4 degrees. Okay, we want to know then how far are we from where we really should have been? Well, if this were our line of travel that we were supposed to be, we want to know then this distance. How far are we from where we actually should be? Where did we end up in comparison to where we should have ended up? So we can look at this. We have an angle. We're looking for the opposite. We know the hypotenuse. So we can use the sine. So we would simply say the sine of 2.4 is equal to the opposite over the hypotenuse. And we can put that into our calculator. 36 sine of 2.4. And so we're going to be 1.5 miles off course. We're going to end up 1.5 miles away from where we should have. And you can then see how important it is if you were a plane and you were traveling a lot faster, then you would be much further off course just by being off just a few degrees. Okay, let's look at this. We're just going to talk about a vector and its horizontal and vertical components. So here we have a vector that has a magnitude of 17.6, and it has a direction, its angle of 67.2 degrees with the horizontal. So if we have our horizontal, then our vector is going to have an angle of 67.2 degrees and a magnitude of 17.6. So we have 67.2 and a magnitude of 17.6. Now, often what we want to find is the horizontal and vertical components. And that simply means that our vertical component would be down to the horizontal line. It's like finding our x and our y. In fact, we will actually call this this would actually be v sub y because it's our vertical component, and this would be v sub x would be the name of this one, our horizontal component. And so we want to find these. Well, all that we're actually doing, we have an angle. We're wanting the opposite over the hypotenuse. So we would use the sine of 67.2 is equal to v sub y over 17.6. So 17.6 times the sine of 67.2. If we put that into our calculator, then that's going to give us 16.2 would be the magnitude of our vertical component. To find our horizontal component, we would, which means I should have put that in absolute values, then we would use the cosine. We're looking for the adjacent, the hypotenuse, so the cosine of 67.2 is equal to v sub x over 17.6. So if you put that into your calculator, I'm just kind of leaving that up to you to put it in your calculator, we would get 6.8 would be the magnitude of v sub x. And you can see that y should be a lot longer because we have an angle greater than 45 degrees. So our horizontal should, our vertical should be a bigger component. Now, we could have our horizontal and vertical vectors, and we might want to find the magnitude of v. So if we drew our vertical, our v sub y, well, let's start with our v sub x. Then it's 45. Our v sub y, or our vertical one, is 15, so it's a lot shorter. And what we want to know then is what is v. We know the horizontal and the vertical in this case. So this one was 45 and this one was 15. So what we want to find is the magnitude of v, so we simply use the Pythagorean theorem. So 15 squared plus 45 squared would equal v squared, so the square root of this would be the magnitude of v. And again, I'll let you put that into your calculator. So we get that the magnitude of v is 47, and actually 47.4 would be the magnitude of v. So you can be asked to find different parts of your magnitudes. Okay, we've got a problem. A bullet is fired into the air with an initial velocity of 1,600 feet per second at an angle of 60 degrees from the horizontal. Find the magnitudes of the horizontal and vertical components of the velocity vector. So this problem is fairly similar. We've got it's fired with an angle of 60 degrees from the horizontal. So let me draw a horizontal, and it's 60 degrees from that, and it's got a velocity of 1,600 feet. So we want the magnitudes of the horizontal and vertical components, and we're going to assume after 1 second. And basically what we're finding then is how fast they're changing. How fast are we changing horizontally compared to how fast vertically? Okay, so we know that our angle was 60 degrees. This one was 1,600 feet. And so we want to find our horizontal v sub x and v sub y. We can actually find these exactly because we've got a 60-degree angle. We know that the sine of 60, or we can even use the ratio that we did before. Well, let's just look at it both ways. The sine of 60 is equal to v sub y over 1,600, or 1,600 times the sine of 60 equals our vertical component. Now the sine of 60 is the square root of 3 over 2. So we could cancel and we get 800 times the square root of 3 equals our vertical component. The cosine of 60 would be our horizontal component over 1,600. So 1,600 times the cosine of 60 equals v sub x. Cosine of 60 is 1/2. And so 800 would be the magnitude of our horizontal. So basically, it's changing at a rate of 800 feet per second. And our vertical one, if we needed an approximation, is changing at a rate of 1305 feet per second. Would be approximately that. And since it's fired at that angle, you could see that it's going up in the air faster. It's doing a greater vertical change than it is horizontal change. Now you could have also found, if you wanted to, from this, you know the side opposite the 60 is the short side times the square root of 3, so we could have set it up that way. The side opposite the 30-degree angle is half the hypotenuse, so it would have been 800, and then this side is that short side 800 times the square root of 3. And we could have solved it in that way. When it turns out to be one of our special angles, then we want to look at ways that we can go through and solve it if we can solve it easier. Okay, we have a ship travels in the direction of south 15 degrees east for 72 miles and then changes its course to south 50 degrees east for 120 miles. Find the total distance south and the total distance east that the ship travels. Well, start out by drawing. Let's do our north-south line as kind of a reference point. Okay, it's going to go south 15 degrees toward the east. So going off in this direction for 72 miles. Then it changes directions and it's on a course of south 50 degrees. So let's draw our north-south lines again. And now it's going to change directions and it's going to go south 50 degrees toward the east for 120 miles. Now, what we want to know is how far south are we and how far east are we now at that point? Let me just extend these lines here. We want to know how far south we are and how far east we are at that point. Well, what we have to do is to break this into two triangles. So we can find out how far south we are for this triangle and how far east we are. Then for this triangle, we can find out how far south and how far east we are, and then just simply add them together. So let's look at the first one. Let's call this, just so that we don't get them confused, we'll call this one S1 and East 1. And then we'll call this S2 and East sub 2. Because we're just going to have two separate problems. Now for this one, we know that this angle was 15 and this was 72. For this triangle, we know that this angle was 50 degrees and this distance was 120. Okay, let's start with S sub 1. We know our angle, S sub 1's the adjacent, we know the hypotenuse. So that would be the cosine of 15 degrees is equal to the adjacent over the hypotenuse. So 72 cosine 15 equals S sub 1. Which would be 70. So I went 70 miles south. For the east, which is actually our horizontal component, well, for our angle, east is the opposite and hypotenuse, so that would be the sine. So the sine of 15 is equal to the opposite over the hypotenuse, or 72 sine 15 equals the east distance, which would be 19. Now if we go down to our lower triangle to find the south, well, that's the adjacent, the hypotenuse, so we would use cosine. So the cosine of 50 is equal to the adjacent over the hypotenuse. Which would be 77. For the east, that's your opposite side and hypotenuse, so that would be the sine of 50 equals the opposite over the hypotenuse. Which would be 92 miles. So for the distance south, we want to add S sub 1 plus S sub 2. So we're 147 miles south. For the east, we're 19 plus 92, which is 111 miles east of where we started. So there's a lot of different problems that you use your horizontal and vertical components uh, to find. All right. Now we want to look at some things that deal a little bit with your physics and with forces. And so we have a definition that when an object is stationary at rest, we say it's in a state of static equilibrium. When an object is in this state, the sum of the forces acting on the object must be zero. So if we go through and we're adding them up, the way that that picture would kind of look when you start adding them is you would have one force, then added to another force. It gets you back to the beginning so that the sum of those is zero. And we'll look at some problems as they deal with that, but this is kind of how our vectors will look, is you'll have a force and then another force acting upon it, and the sum of those vectors is zero. So we're going to look at some classic type problems with this, and one of them deals with the swing. Billy weighs 50 pounds and is sitting in a swing. Brenda pulls him and the swing back horizontally through an angle of 30 degrees and then stops. Find the tension in the ropes of the swing and the magnitude of the force exerted by Brenda. So if we thought of a picture of this, and we're going to draw this several ways when we start doing this, but what ends up happening is Billy's sitting in this swing, his weight's holding him down. Now, Brenda's going to take him and she's going to pull him back horizontally. So she'll pull him back until he's over here. And we've got the rope acting upon that. And then his weight is still going vertical to the ground. And we've got our degrees that are, she's going pulling back at a certain degree. And so she's exerting a force in this direction, pulling him back. The rope has a tension in it, exerting it in this direction. And then his weight is pulling him down. So we've got these three forces, but since he's at rest, she's pulled him back and is holding him there, then all of those, the sum of them are zero. So let's see how we would draw this so that it would make a little bit more sense to us of what we're doing. Okay, we know that his weight is always going perpendicular to the ground. So we've got his weight holding him back. Holding him, and went off of perpendicular. Okay, when Brenda pulls him back, she actually pulls him back horizontally. Her arms are going horizontally. So she's going to be acting in this direction with some force. And then the tension in the rope is holding him there because she's pulling him back and that's keeping the rope taut. And so we've got the tension in the rope. Now let's label what we know. His weight was 50 pounds. And we know that the angle between him, which that would be his weight, and the rope, she pulled him back at a 30-degree angle and then stopped. So what we want to do is to find the magnitude of the force. How much force is she exerting, which would be our horizontal component, if you wanted to think of that, but the force of Brenda. And then what was the tension in the rope? We'll just call that T, because he's being held up. She's not having to lift him off the ground. The rope is still holding him up. So those are the ones that we want to find. Well, if we want to find the force that Brenda's using, that's the opposite. Uh, his weight's the adjacent, so that would be tangent. So the tangent, and again, since this is a 30-degree angle, we know that this side's half the hypotenuse and this side is the short side times the square root of 50. So we could put in our ratios and find it, but it won't always be a 30-degree angle, so I want to go through and work it. The sine of 30 is equal to V sub b, Brenda's vector, over 50, or 50 sine 30. And we know that the sine of 30 is 1/2, so this is going to be 25. So Brenda is exerting 25 pounds of pressure. That's her force. Now the tension in the rope, that would be the adjacent over the hypotenuse. So that would be the cosine. And I did that wrong, didn't I? Because this should be a tangent. So let me just go back and change it before we move on. Should be the tangent of 30. It's the opposite over the adjacent. And so that would be approximately 50 times the tangent of 30 would be 29. And you say, well, we don't usually use our calculator when it's a 30-degree angle. But if we said tangent of 30 square root of 3 over 3, so we'd have 50 times the square root of 3 over 3, and understanding that in pounds doesn't make a lot of sense. So when we're in our applications, we usually want to go ahead and get an approximation. Now, here we know the adjacent. We're looking for the hypotenuse, so that would be the cosine of 30 is equal to the adjacent over the hypotenuse, doing our cross product. So the tension in the rope is equal to 50 divided by the cosine of 30. Which would be 58 pounds of pressure. Okay, so this would be an example of where we have some forces and we have some tension working on that. Let's look at another problem that's similar to that. We've got a 15-pound weight is lying on a sit-up bench. If the bench is inclined at an angle of 12 degrees, there are 3 forces acting on the weight. N is called the normal force, and it acts in the direction perpendicular to the bench. F is the force due to friction that holds the weight on the bench. And if the weight does not move, then the sum of these 3 forces is 0. Find the magnitude of N and the magnitude of F. Okay, we've got us a sit-up bench, and it's at an angle of 12 degrees. So if this were the floor, then our bench is at an angle of 12 degrees. Now what we have on that bench is a weight. And so the weight, remember, weight always goes perpendicular to the ground. So the force acting upon the weight would be here. So we have our weight, And it told us that the weight was 15 pounds, so we know that force. And we know that our angle is 12 degrees. Okay, then we have a normal and we have the friction. The normal, it said, is perpendicular to the bench. So it's going off perpendicular to the bench, and that would be N. So this would be a right angle. And that would be N. And then we have friction, which is what's holding the weight in place so that it doesn't slide off. And so our friction is actually going then parallel to the bench and is holding our weight up. And so we have our friction. Didn't do too well. Now, when the weight just stays there and doesn't move, then it's in a state of static equilibrium. So the sum of these would be 0. So what we want to do is let's redraw this so that we can see where it would go. And so what we deal with is our friction. It's holding it in place. We're going to let that be perpendicular. The norm is perpendicular to the friction. And then the weight would be the sum of those. Okay, so if we look at what we have, then we've got our weight is 25. Now, our angle was between the weight and the friction. That was what was at a 12 degree, and that's kind of what's acting against the friction is the angle, and our angle was 12. So what we want to find is what the norm is and what our friction is, what forces they're using upon this. So the norm would be the opposite over the hypotenuse. Opposite and hypotenuse is sine. So the sine of 12 is equal to the opposite over the hypotenuse. So that would be 5 pounds. And then our friction, that's going to be the adjacent over the hypotenuse, so that would be the cosine of 12. Which is 24. So that would be 24 pounds of force. Dealing with the friction is what we would have that holds the weight in place. And some of this gets a little beyond, it gets into physics, and probably your physics teacher could give you a better explanation of how these different forces act. Okay, then if we look at this problem, let me move it down just a tiny bit. This is another definition that goes back into physics. It says if a constant for F, for if a constant force F is applied to an object and moves the object in a straight line a distance d in the direction of the force, then the work W performed by the force is work is equal to force times distance. Okay, this is our definition for work. And notice you can apply a force on something, but if it doesn't move any distance, then there's no work done. And so work is the force that we're using times the distance that it's drawn. And if you go back to some early definitions, and again, I can't give you a technical one here, but horsepower dealt with how far a horse could pull something, a certain weight, in an amount of time. And so it was dealing with work. So we're going to look at a problem that deals with work and how we would go about figuring out how much work was done. So let's look at this problem. A desk is pushed across a floor a distance of 40 feet by exerting a force of 12 pounds downward at an angle of 30 degrees with the horizontal. How much work is being done? Okay, we have a desk, and we could think of this as some object that we have. And what we want to do is to move that desk. Now, when we push on something, we don't push straight down and we don't push horizontally. As we stand there, we're pushing at an angle. And so we're going to have our angle here. And it said that we're pushing at an angle of 30 degrees with the horizontal. So if we had our horizontal line, then we're going to be pushing at an angle of 30 degrees with that horizontal. Now when we do, the desk is moved horizontally. It's not moved in this direction. We're pushing it across the room, across the floor. So the desk goes horizontally, but our force is going at an angle. And if you'll stand there and try to push at something, you'll see that your arms make an angle with the floor, and you would still push it horizontally, but you're going to be pushing at an angle. So we've got an angle here of 30 degrees, and we're pushing with a force of 12 pounds. So what we want to know is what force is acting upon that desk, because some of this 12, it goes down, some of it goes horizontally. So we can picture that there's a right angle here because we've got force going in both directions. We have a horizontal and a vertical component for that force. So we want to know what the horizontal component is. Well, in doing that, we've got an angle and we have the hypotenuse. We're looking for the adjacent. So again, we would use cosine. And again, I'm going to go ahead and work it out even though we know it's 30 degrees because it won't always be 30. So the cosine is the force over the hypotenuse. So 12 times the cosine of 30 equals our horizontal force. So 12 cosine of 30. So that's approximately 10. So we have 10 pounds of force. But we want to know how much work is being done. So work, if you remember, was the force, which is 10, times the distance, and we pushed it for 40 feet. So our work would be 400, and we call this foot-pounds. That's why work is always measured in two things. It's how far you pushed it and how much force was applied. So we actually dealt here at 400 foot-pounds. So these are just some different applications of our vectors acting in several different ways.